Hello and welcome to High Water Studio. In today's lecture, we're going to talk about how to determine mixed stream concentrations performing a mass balance. Stream mixing is basically when you have either two streams merging together, obviously, but it could also be when you have some kind of a concentrated flow. So a good example of that would be when you have the waste stream from some sort of industrial process, or when you have concentrated stormwater runoff being discharged to a receiving stream. And so we're going to be looking at how we can use mass balance to determine what these mixed concentrations would be. And basically what that is we're going to be using a weighted average, using an average of the concentrations weighted by the flow rates for each stream. And one of the assumptions that we are going to be making with this type of calculation is that we're going to have an instantaneous mixture, an instantaneous and complete mixture, which is pretty typical for this type of calculation, since you don't usually get a heterogeneous type of distribution of concentrations across your stream anyways. So, as we mentioned, we can use this for point source loads, and also we're going to be talking about the continuity equation, which is basically using the conservation of mass to determine downstream flow rates, and also later velocities, and also looking at the concentrations in terms of a conservative pollutant. And what that means is basically the concentration will be preserved or conserved. It's not going to be lost due to any kind of decay or sorption or volatilization. Okay, so graphically what we're looking at here is that we have this stream with a large flow rate and low concentration typically, and you have a waste stream merging with it that generally has a low flow rate but high concentration. And we want to determine what this downstream concentration is going to be. So what we are going to do is use this mass balance equation where our downstream concentration is going to be this weighted average, right? So we have our concentration and our flow rate here for the stream, which basically gives us a mass flow rate, and are weighted with our waste stream concentration and flow rate, and divided by this downstream combination, this mixed flow rate. And because of continuity, we know that the flow rates are always going to be additive when you have sources, and of course they would subtract if you had some sort of a loss, because there can't, unless you have storage, like in a reservoir filling up or something like that, these are always going to be added up to a downstream flow rate. That's going to be the sum of its parts. So we're able to take this expression, substitute it into the volumetric mixed flow rate, and then we get this final mass balance equation that can be solved for our downstream mixed concentration. So just putting some numbers in here, we said typically we get a low concentration, high flow rate for your stream, high concentration, low flow rate for your waste stream, in this case 50 milligrams per liter in 3 cubic meters per second. And putting those into our calculation here, we can see this is our stream mass flow rate, our waste stream mass flow rate, our combined mixed stream volumetric flow rate, and just kind of clearing that up a bit, that leaves us with about 10.9 milligrams per liter. Okay, well, thank you. I hope that was helpful if you were trying to determine how, or interested in how, these mixed stream concentrations are determined. Now remember though that is only for conservative pollutants or non-conservative pollutants at the moment of mixing. If you want to determine downstream concentrations for non-conservative pollutants, we're going to need to start talking about modeling decay and determining velocities and things like that, which will be in our next episode. Thank you very much for watching.